we have one final and important process to consider, which is stimulated emission. This process is strong in laser light, though it's actually also present in small amounts all the time. Einstein realized this process had to exist, and he did this before anyone had any real understanding of how the quantum mechanics of light emission would work in detail. He came up with a famous approach called Einstein's A and B coefficient argument that got all the right answers. He made some simple assumptions about how the processes probably could be described and required that the statistical mechanics of light agree with observation when we're considering thermal equilibrium. We won't go into that argument here, though it is interesting to read it. Instead, we will explicitly derive stimulated emission from our quantum mechanical model, without requiring those thermal or statistical mechanics arguments.
So now we're going to look at stimulated emission. As before, we have our two electron levels here. Suppose now we have a photon in mode lambda 1 and an electron in its upper state 2. The initial state, therefore, is our photon in mode lambda 1, so a creation operator for that, and our electron in state 2, so a creation operator for that. And that will have an energy that corresponds to E2 plus the photon energy. Then, with algebra similar to that we've used before twice already now, this string of operators that we will obtain with our starting state and our perturbing Hamiltonian here will simplify to this here. The first term is simply the absorption term. Note that there are no photons left here and the electron is in some state J. But this term is going to vanish because there is no electron state into which we can absorb, because we've chosen that we're starting in state 2. So that one is going to disappear because there's no other state into which we can absorb a photon to transition into it. So the second term has two possibilities in this summation that it's going to finally appear in. One is that we choose this mode lambda to be different from the mode lambda 1 of the original photon. And the other possibility is that we're going to choose lambda to be the same as the mode lambda 1 that the original photon was in. So this happens in our summation here. We end up summing over all of the possible modes, and we have two different possibilities. Either the modes we're looking at are different from the starting mode, or they are the same. So suppose that we're talking about different modes. This was the mode that our first photon was in when we started, and we're talking about possibly having a photon in another mode. So in that case, this term here, this 2/3 of our perturbing Hamiltonian matrix element, becomes this string of operators. A photon in mode lambda 1, a photon in mode lambda, and the electron in state J. So that just comes from our algebra, given that we're choosing lambda to be different from lambda 1. Then, for some specific mode lambda that is going to be different from the mode that the original photon is in, to get a non-zero result for our final matrix element, the final state is going to have to be this one, so that it's the same as that, so we get a non-zero result. And that's going to have energy of whatever electron state the electron is in, so whatever J is going to be here, the energy of this photon in mode lambda, and the energy of this photon, the original one, in mode lambda 1. And that corresponds to a state with the electron in level J and a photon in each of the different modes, lambda and lambda 1. We'll have, for some specific mode lambda and some specific electron state J, this form here from our perturbation theory. Because of our choice of the final state here, of course, this just evaluates to 1. And so we're left with this expression here. And if we integrate that up and square it as before and divide by the time we're integrating over, we will get this kind of Fermi's golden rule transition rate. And the only possibility here for a non-zero transition rate, that is, for the delta function to be anything other than just 0, is if we choose J, the electron final state, to be 1, and choose the energy separation, E2 minus E1, and the emitted photon energy, h bar omega lambda, to be equal to one another. This process is just spontaneous emission again into mode lambda, with the same transition rate as before. So this process starts with the electron in state 2, a photon in mode lambda 1, and ends with the electron in state 1 and a photon in mode lambda 1 and also a photon spontaneously emitted into mode lambda. This spontaneous emission process that we've just calculated here in mode lambda is actually completely unaffected by the presence of the photon in mode lambda 1. And this is generally true. Spontaneous emission into some mode is not affected by how many photons there are in other modes. Now, however, let's look at the situation where the final two photons are in the same mode. So we're supposing that lambda and lambda 1 are the same mode. So the right-hand 2/3 of our matrix element leads to a term like this. We have two creation operators for the same mode and the electron creation operator for single particle state J. So this set of terms emerges from here. So to get a non-zero result for the entire matrix element, the final normalized state has to be essentially this one, but be careful here. We have to choose a normalized state here, of course. And that normalized state looks like this. So this is the normalized state with two photons in mode lambda 1 and the electron in single particle state J. That has energy, Ej, whatever our electron state is, plus 2 h bar omega lambda 1. But note that to have a normalized state here, we have had to introduce this factor 1 over root 2 factorial, as in the general normalized multiple boson state. This is very important here. It comes from the creation operators. If we didn't put in this factor 1 over root 2 here, this remaining term would actually not be normalized. Hence, from this matrix element, we are obtaining a term that looks like this, and we can rewrite that, putting a 1 over root 2 factorial in with this half, if we like, and compensating by putting a root 2 factorial out the front here. So this is going to evaluate to 1 because it's the inner product of a state, a normalized state, with itself, another version of this normalized state. And so this evaluates to root 2 factorial, which here is the same as root 2, times this number here. As we said, this root 2 is very important. It comes from having two photons in the same mode and leads to a larger amplitude for this process than for spontaneous emission. Hence, for this process, we have our usual kind of expression here, but we've acquired a root 2 in here, and that leads to a transition rate into this final state, whatever that is, choice of J still to be determined here, in this form, but with a 2 in here coming from the square of this. And of course, the only possibility if we're to have finite transition rates is for J to equal 1 and for E2 minus E1 to equal h bar omega lambda 1. And that will have a corresponding transition rate, finally, of this here. It's almost the same as we've seen before, for example, for spontaneous emission, but we have a factor of 2 in here now. So this process starts with the electron in state 2, a photon in mode lambda 1, and ends with the electron in state 1, two photons in mode lambda 1, as we see here. This process is called stimulated emission. Note the additional factor of 2 in the transition rate. Note that other things being equal, that is, matrix elements and energies, the transition rate into the mode already occupied with a photon is twice as high as the spontaneous emission rate into an unoccupied mode. Bosons want to go into modes that are already occupied. We could carry this on to a multi-photon case, and we'll leave this as an exercise to analyze the case where we start out with n lambda-1 photons initially in mode lambda-1. The result for stimulated emission is simply this result here. We've got a factor n lambda-1 plus 1 here. Remember, that was 2 when we put 1 photon in the mode, so for n lambda-1 equal to 1, indeed we get 2. But if we analyze this case with n lambda-1 photons in the mode to start with, then we end up with this factor n lambda-1 plus 1 in the transition rate. Note that therefore this transition rate is n lambda-1 plus 1 times larger than the spontaneous rate into an otherwise similar mode. Spontaneous emission in any other mode, lambda, is unaffected by the presence of these n lambda-1 photons in mode lambda-1, which you could check now. And we could show this directly by considering this multi-photon case. The result for absorption, when we start out with n lambda-1 photons initially in mode lambda-1, can similarly be shown to be a transition rate like this, with a factor n lambda-1 in here, where the absorption rate is now seen to be proportional just to the number of photons in the mode. For the stimulated emission, it was that number plus 1. And this, of course, is as we would expect. We would expect the absorption transition rate to grow with the number of photons in the mode. Note specifically in the absorption transition rate, then, that we wrote the matrix element in this form, ED lambda-1, 1, 2, not the matrix element ED lambda-1, 2, 1. Given the definition of these matrix element numbers here, these integrals, we see that swapping around the 1 and 2 here just gets us a complex conjugate. And so the modulus squared of these matrix elements doesn't care which order we put these numbers in. So we can just choose one order to write this down when we put it inside the transition rate.
The relation between the absorption and stimulated emission strengths is fundamental, as is their relation to the spontaneous emission strengths. There is only one set of matrix elements involved in all of these processes. Once we know the absorption strength of some transition, then we can also know the strength of the stimulated emission in a given mode. With some knowledge of the electromagnetic modes in the region round about the emitter, we can also calculate the spontaneous emission processes. To complete our story here, we'll next make some assumptions about those electromagnetic modes into which we can have spontaneous emission. That will allow us to calculate the entire process of spontaneous emission by which an atom emits light under most circumstances.